Okay, let's get back. Well, before I talk about the slides and also just content on the coding reduction for unsupervised learning, also derive the white box transformer, I want to first briefly introduce a methodology like to do the optimization analysis or more specifically, that is loss landscape analysis I have mentioned here for some loss function for the deep learning. In general, when you read some paper or some right in some textbook, what you met is like some objective function, right? Maximize some neural network, right? The data and something like this, whatever. This is input, and you have lots of input, right? The data, and this, or maybe I use the notion here is not is better. I use this notion. That is okay, right? You may some optimization like this. The input is X, right? After the transformation by the neural network, theta, right? After transformation by the neural network, this one denote neural network F theta, right? And this is the features you learn by neural network. And this is the training loss, like training loss usually the right is imposed on the learned features, and this theta is network parameters. In general, that is the training problem we met in practice, right? But if we want to do some analysis, on this problem, is there some significant difficulty due to what? Due to the neural network architectures, it may contain lots of parameters and also have many nonlinearities, right, in the network architecture. Like, for example, this one is the transformer, or maybe UNet, different neural network architecture. It's almost impossible, like, to do, like, I want to analysis, like, do compute this one, right, to be zero, like, analyze the first optimality. Then how to handle this if you want to do some theoretical analysis in your paper? How to do it? Actually, in this book, or like in our recent research, we proposed a way to, in some sense, to get around this difficulty. That is to like consider in the all parameterized setting, all parameterized, right? I think most of you guys may heard about it. What is all parameterized setting? That is network parameters, right? Is much larger than the number of samples, right? In this case, the neural network here, for any output, right? You can learn any output because neural network is highly optimized. Given any output, you can always find some input such that after transformation by the neural network, you can get the output. You know what I mean, right? When the network is highly optimized, it's like a linear system with the number of variables is much larger than the number of constraints. You have infinite solutions, right? You can find a set of parameters such that you can find some solution. You can get some solution. That is same spirit. So here in the open setting, then you can view this Z to be a free optimization variable and no constraints on the Z. So here you reduce a neural network based problem to what? To like a free optimization variable problem. Just to focus on analysis for the optimization. When the optimization variable is what? Is repetitions, right? And no constraint on the repetitions. Originally, we have this, right? Like this one. But now, because network is highly optimized, we can remove it. It directly analyze this one. And although this is like an approximation, but in most of cases, especially like we said, open setting, you will find the solution derived here. The solution derived here, like use the first optimality analysis or second optimality analysis, you will find is very, very close to what you find to optimize the use like the backpropagation or like this different algorithms, right? So category stand use backpropagation for solving the original problem. Training neural network is very close. Like in this case, what we said, the solutions here is like close, like reputations here we found is like orthogonal to each other, right? That corresponds to consists of a family of subspace, right? That corresponds to a family of orthogonal subspace. And actually, in practice, you will empirically find that the reputations you learned is close to the family of orthogonal subspaces. So this approach provides a good, right, understanding on the deep neural network based training problem. So it's like just approximation approach, not the exact approach to do analysis. Okay. Any questions? If not, we go ahead. Okay. We just talk about the sparse rate reduction, right? Use sparse rate reduction. This is an objective function to do unrolling and construct the neural network. Well, now we will show how to derive this incremental and local operators through an unrolled optimization perspective to optimize this sparse rate objective function, right? Once we decide on using an incremental approach to optimize these problems, there are lots of different choices to achieve the optimization. And here we introduce one of them, right? We use a two-step alternative minimization to optimize this features, right? So here, the first step is to do what? We compress these tokens well gradient descent to maximize this compression term, right? That is the first step. And then in the second step, we do what? Specify the compressed tokens, generating the ZL+1, right? The second step here, you can see this is like a suitably relaxed proximal gradient step to optimize this RZ, RL1 norm of Z minus RZ, right? Okay, now let's take a look at the details. The first step, compression step. And based on step, actually, we can construct a multi-hat subspace self-attention. Okay, we go to see the details, right? The first step is the main ingredient is doing what? Is to compute, right? The gradient of this compression term, right? To compute this, the gradient of RC, that term, right? So you can use the rules and compute it explicitly. This gradient is like this form. That is the summation of K from 1 to capital K, right? Euclid transpose Z, and this is matrix inverse. Matrix inverse is not we want to expect, is not our expect, right? It's really complicated to handle. So here we use a clever approach as doing what? It's use a Newman series, first order Newman series. Newman series, the equation is like this. Identity minus square matrix A, and the inverse is like right. We view this as A. Newman series, it means we do expansion as follows. K equals to 0 to infinite. This is Newman's equation, Newman series. Summation of A K's power until from K to 0 to K to infinity. Okay. And actually, we have some A square, okay? Must be square, right? So, and we have another assumption. You can expect is what? You can imagine is what? The norm of A must be spectral norm less than 1, right? Otherwise, it may blow up if your summation from have infinite the terms of summations, right? So here we have assumption. The exercise in our book, this is exercise 4.2 in our book. And this type is the exercise on the book that is starting from K equals to 0, notebook from 1. In the book, there's type there. Okay. So apply this Newman series expansion right here, this equation, we can get an approximation of this step, right? Apply that, right? That is identity minus this A, right? Okay. Apply Newman series, this expansion to here, then we can get this step. Any questions? To avoid computing the matrix inverse, right? We apply the Newman series to get a first order approximation and then get that there. That one is the approximation of the gradient of this compression term, right? Then we further make assumption that is all the subspace here spans the whole space. All the subspace, that is the UK transpose summation here to be identity. Then this term summation here is what? Z. Right? You can see here U transpose, right? Apply this equation, and then this term is Z. And the remaining one, we reorganize it. We will see in the next page how we reorganize it and then get a multi-subspace self-attention. Okay, and here this is like what? It's like residue connections, right? If we like take a gradient step on the objective, on the optimization, on the representations, right? The induced like residue connections. Okay, first we took a look at the multi-head subspace self-attention, right? And I think most of the guys have saw this, right? Have saw this. That is multi-head standard attention. Multi-head, the standard self-attention, right? Multi-head. It's like take of this formula. That is, this is output matrix, right? And this is head 1 until head k. And this is like WO is to do a linear combination of these different heads. And each head, the formula is like this. These features, right? The output of some layer, they transpose the key matrix, right? And this is query matrix, this is key matrix. And this is the value matrix, right? This is standard self-attention. But different from the standard self-attention based on our principles, right? Optimizing the take gradient step for the compression term, we will have this subspace self-attention. You can see here that is reorganize this thing here, this thing here. We will go from there to here. That is like U1 to UK times this matrix times each color, each row is like this operator, subspace self-attention, and it's UK transpose Z and times UK transpose Z, UK transpose Z. And here, this softmax is what we impose here. If we directly use the original, this formula, what do we have? What do we will have? Just the linear tension, right? Subspace linear tension, right? Not we won't have softmax, but here to better capture like the membership relations, right? The similarity of different projected tokens. We add a softmax operations here to convert UK transpose Z transpose UK transpose Z, this one, to be a distribution of a membership. And then we obtain the multi-head subspace self-attention. Can you see the connections between these two operators? Multi-head subspace attention and the multi-head subspace self-attention. Actually, it's very straightforward, right? If we take WO equals to WK, WKV, and also equals to WKQ equals to WKK, right? This one, all of them are equal, and equal to what? To be U1 to UK, right? Then we can recover the multi-head subspace self-attention, right? So that is, in some sense, multi-head subspace self-attention is like a special instance of multi-head standard self-attention by restricting of what? By restricting the key value, right? Key value query matrix to be same. But difference is what? But here multi-head substrate self-attention is derived from where? From the compression term, right? Optimizing the compression term of the maximum coding rate is principally proposed, designed. Actually, the self-attention, this idea, I have to say is very clever, right? It's really intelligent, this design, this one. But when some others, like I just heard a story online, some people like in attend a conference, and one of the author of this paper, that is, the self-attention, this paper is attention is all you need, right? That team or author attend a conference, maybe Europe or ISML. Some others ask them, how do they think about this idea? What's the motivation to design this operator? They say, what are these like? What are these authors? They just the answer is, they read a lot of paper and try heuristically try different architectures and finally found this works best, and then they propose this architecture. No theoretical insights actually. Okay. Well, and then we go further. And that is to sum up what we have, right? To sum up what we have introduced in the previous two slides, right? But then we can get the compression step, multi-head subspace self-attention block. You can see here to get an intermediate output, right? It's like this one is like a residual connection plus multi-head subspace self-attention. And the details is like this. You can see here. At the else step, right? The block, the transformer block at the else step, the else block, the input is the L. First we do a Néel normalization, then goes to this multi-head self-attention. This is the residual connections here. And inside the multi-head self-attention, this block, it consists of the operators here. What do we, specifically, this details, the formula is here, you can see, right? It's like lots of the attention head, one K had one until head K, right? And do a linear combination to get the output, right? And inside each head is multi-head subspace attention. That is the whole, the whole map of the one attention block. And it's like one step of the one block of the standard transformer block, right? The attention. And the main difference is here, there is no separate query and key value matrix in our constructed transform block, in this white box transform block. Okay, any questions? Now we go ahead to the second step. We apply the alternative minimization. We get the second step. That is, like we said, we do not directly, here we do not use the approach, right? Direct approach to apply the proximal grid stat to optimize the specification of the term. Since we cannot get a good updates here, and cannot construct a very satisfying architecture. Here we do like an implicit approach. We conjecture that the incoherent, the complete incoherent, incorporate actually means orthogonal dictionary. There exists such dictionary DL, and we want to use it to specify the intermediate, this output of the last step, right? The output, and then that is the output of this step is DL plus 1, and this is the intermediate output approximately equal to this orthogonal dictionary times this DL plus 1. It's like do a decomposition, right? Use the dictionary, and then since this dictionary we impose it to be, right, assume it to be the orthogonal, then under this dictionary the transformation, the orthogonal transformation, it won't change the value of this coding rate. So to optimize under this setup, right, to optimize this objective function, it approximately to optimize the following problem: minimize this L1 norm, right, to impose the sparsity, and well keep the value, this value doesn't change by impose this constraint. We go from that one to here. Then we further consider apply a gradient proximal gradient descent to optimize this. That is, we enforced like penalty this constraint, right, to be the objective function, and get this one, and then approximately solve the following problem. Arguing the L1 norm, right, plus the like a mean square norm, mean square Frobenius norm, right? And this one is like what? It's like a Lasso problem. And different from Lasso problem, we also had a non-negative constraint here. And this non-negative constraint is like a normalization, right? To guarantee it's like a ReLU operator. Okay, and then based on this, incrementally optimize the above problem. Yield the following updates. That is ZL plus one, right? Is like apply a E star operator to ZL, the intermediate output, ZL plus 1/2. Okay, and this E star operator is like the proximal gradient descent to the objective function we just introduced, Z minus this one and minus eta times lambda times one. This, and this induce the E star block. That is for the specification step. You can see here the figure is like this. We have the output, right? The intermediate step generated by what? Generated by the compression step, right? Multi-head subspace self-adhesion block. This is the input for the E star block. And in the E star block, we have lots of architecture. We have lots of the details, right? You can see these details. First, do like layer normalization and then apply a DL operator here, and then minus this one, right? Minus this D transpose Z, and also do a ReLU operator and get the E star block. This is to mimic the what? Mimic the MLP feed-forward layers in standard transformers. Okay. And to sum up the above, right? The combining the above two steps, we get one layer of the post. The right box transformer, the name is create this transformer architectures. That is coding rate. Let me see. Have I give the full name of this? Seems not. Right. The full name of create is coding rate transformer. For short, is coding, right? RAT, right? Coding rate. This is C. This is RAT. Coding rate transformer. For short, call it create. In the bug. Okay. Then one layer of the coding of this network transformer consists of two steps, right? The first one is compression step. Second is specification step, right? You can see here, this is the whole pipeline of the one layer of create. We first do a multi-head self-attention here. Subspace self-attention is to compress the features, right? And then we do a specification. This E star block, that is to make this like not sparse this representation to be like axis line sparse representation, and then get the one block of this transformer. Okay. And here, this is a visualization of the whole. We combine them together. The previous introduced the block, the architectures design together here to be here. You can see we at else layer, we have some output of the else layer DL, and first do layer normalization, and then go to the multi-head subspace attention rate we have introduced before, and then get the, and here this is residual connection, and then get a intermediate output at ZL plus 1/2, and then do a layer normalization, and then the follows is the E star block, and finally get the output of this layer, and this is a full architecture. And the full architecture is a concatenation of these layers with some other like initial tokalization pre-processing head, right? And also final task specific head, like the classification head. That is the full create architectures. Any questions? Okay, any questions? This is in actually this the grid architecture is really close to the standard transformer architecture, right? Standard transformer architecture, it's not the multi-head subspace tension, it's standard subspace, is standard self-tension, and this block is what is the MLP layers, right? That is standard transformer architecture. Okay. Well, and here, when we construct this neural network, how we to do it? How do we do it? We directly forward minor, right? Forward minor from one layer, two layer, go to the else layer, right? Forward fashion. It's also like the redo net, right? Then forward layer is like to construct the neural network, but when we construct it, right, in forward pass, this subspace and also this dictionary, these parameters like UK and DK, DL, right? The layer-wise the layers parameters at each layer are fixed, and then we construct it, right? Then when we use this neural network for some specific task, how do we optimize these parameters? We need to use the backpropagation. We still use the backpropagation like we have learned in Lista, and Lista, right? When we learn the dictionary in Lista, we need to use backpropagation to train it, right? And at each layer in Lista, the network parameters may be different. And say here is same. We need to use backpropagation to learn subspace and also dictionary learning parameters from the training data. That is the whole map of the backward and forward path of this create architecture, right? Any questions here? Okay. If not, we go further. That is, we do some experiments on the using the create architecture first. Or we do some visualization for the layer-wise behavior of create. You can see here, we simply trained create small this network on the ImageNet 1K data, right? Just train our constructed create architecture on ImageNet, this one, and see what we have when we construct it, right? We say some layers are doing compression and is doing layer-wise compression and specification, right? And whether does this holds in practice when we train or create transformer on real-world data. You can see here. So we train a transformer, right? Then visualize the compression. This metric, this x-axis is number of layer index, and the y-axis is this compression, right? The RCZL, this value. And you can see here as layer increase, the layer index increases, the compression, the metric gradually, in general, right, decrease. That is what we said, the compression. That means it really indeed happens in practice, right? The compression. Although when we construct the neural network, is just conceptually use this idea to construct it. But we can indeed verify this when we train this network architecture on real-world data. And also the specification, you can see here, as the iteration goes, right, the specification, the block specify the sparsity. This is to measure the sparsity of the block. You can see as the iteration goes, as the layer index increase from like 2 to 12, right? In general, the trend of this sparsity, right, the metric, the trend is decreasing, right? From the original sparsity 0.5, and finally it goes to like the 10, 11 layers, it decreased to 0.2. That means create this transformer architecture indeed performs its objective, design objective, right? Each layer incrementally optimize the compression term and the specification term, right? That means we bridge the gap between theory and practice, right? Okay, any questions here? Okay, if not, we go ahead. And now we further do some other experiments, that is to do some visualization of attention in create transformer. That is to visualize attention score, this one. To visualize this one. This classification head, right? Classification, this tokens, the LZCLS, and with some the output at some layers. And the ZI denotes the representation of ICE input token. Okay, and this was visualization, and you can see here that is infinite. This attention score, right? These different heads have some specific the semantic meaning when you visualize it. So we further do a comparison of create semantics of with VIT, the semantics of VIT. You can see here, like for some dogs, right? The create, you can see this is very clean. The framework of the dog images, and also right. And when you saw the VIT, you visualize the attention score of the VIT, you will find compared to the VIT, right? Attention maps of create are much more semantically meaningful for the VIT. Okay. Just some empirical evidence to support our theoretical development. And the next is experiments realization on the further experiment on the realization of attention heads in crate. You can see here, right? On different animals, the attention score, the different heads of the attention score corresponds to different semantics. Like the first, right? The first head 0 corresponds to leg. Head 1 corresponds to the body, right? The framework, the framework of the body, this semantics, and other like head 3 correspond to face of these images, and head 4 correspond to ear, and different images for some other images, right? Also like corresponds to leg, body, face, and ear. It's very consistent. That is what we have observed here, emergence of semantically heads in crate. Okay. And recall that in crate, different heads, we have the main component in different heads is what? Is a subspace, right? UK. And in some sense, just my understanding, this different subspace UK, right? This low dimensional is like a linear span, right? Low dimensional subspace. This low dimensional subspace encodes different semantics of images. Okay, and we further do some experiments on some vision tasks. You can see here, we train the transformers and the standard transformer, vision transformer, right? Like a vision transformer tiny, and the vision transformer base, and also train this vision transformer. Okay, this is size, number of parameters. This is small. This is tiny, just 10 million. This is base 100 million parameters about. And this is a performance that is top 1 accuracy of create and variety on image classification task. Is here. Like this is create tiny. Number of parameters is 5 million. This create small, 14 million. And this is create space 38 million, right? Number of parameters. Compared to the then let's take a look at the performance. Like create small, this one is comparable number of size, of course, a little larger than the VIT tiny, right? The small, but the performance is a little, slightly better than VIT small, right? You can see, you can compare the accuracy here, like this, right? Or like this is base, very close, but slightly worse than variety base. But you can see create base, the non-parameter is much smaller than the variety base. Okay, that is, and also do some other task like a supervise the train, the self-supervised create and variety pre-train on some image net. That is like a K nearest neighbor, and also like it's like this is like the linear probing, right? Compare the create small, create base, and the VIT small, right? With different layers. In general, we can make the following, draw the following conclusion that is great, achieves comparable performance compared to engineered transformer, standard transformer like VIT, right? On different data sets and different tasks. Okay, that is the all the results on the create, and that is. Any questions? Any questions? Okay. If not, we go further. We go to the some variants of deep architectures by design according to our principles. Well, so far we have provided, right, some competing evidence that the rule of deep neural networks, right, is to realize some algorithms, optimization algorithms for minimizing the coding rate reduction, right? However, if you are familiar with optimization method, you will notice that the above architectures like the create and also like the redo-net, right, corresponds to some basic optimization techniques. They have plenty of room for improvement, and also have some other interpretations. And here we mainly introduce two variants of primitively designed create. The first is the attention-only transformer, and we also interpret this one. The transformer is doing this attention-only transformer is doing denoising token representations. So before we go ahead, we take a look at the model for the tokens for the initial token representations. Of course, this is like a idea simplification for the real-world token representations. We assume what? We assume the initial token representations, like the representations we learned by transformer after the token embedding and position encoding. Okay, assume it to do what? Satisfy this assumption. It lies on a union of noise, is like a mixture of noise, Laurent Gaussians. Compared to the previous, the mixture of Laurent Gaussians, we have what? Have a noise term, right? And note that C1, capital C1, CK is a partition of the index set, right? And if I belongs to this case set, then this ith token at the initial layer satisfies this one. This is signal part. This is noise part. Okay. Of course, this is rather like a simplification. The ideal assumption on the real world initial tokens, right? And like we said, because why we can make this, we have some empirical evidence. The first one is the linear hypothesis, linear representation hypothesis. That is, token representations can be linearly encoded as one-dimensional future vectors. Is from this last year paper. They do lots of empirical study and found that this and make a conjecture that is linear representation hypothesis. And the second is superposition hypothesis. That is, we assume that we conjecture from this paper. The conjecture is the token representations are a sparse linear combination of these future vectors. Okay. Then based on this model assumption, we can give a very interesting a theoretical interpretation for the create the multi-head subspace self-attention this operator. Like at the input layer, at the first layer, sorry, this should be the one like this is futures, right? Is near some linear subspace, but not lies on subspace because is perturbed by this noise. And then what essentially this layers of attention, self-attention operator, multi-head self-attention, this operator do is like do a layer-wise denoising, right? You can see the distance from some point here, right? The distance from the subspace gradually decreasing as number of layer increase. Okay, we interpret multi-head subspace self-attention this operator as a denoising operator. Okay, and we have introduced this operator before, right? The multi-head subspace subattention. I won't repeat it here. And the whole architecture we induce based on the attention, based on this multi-head subspace self-attention is like this. We don't have that like what like MLP layers, we won't have it. We directly do like input some and else layer have some DL and layer normalization and do a multi-head subspace, then get the output. This is web connection, right? So different from the current architecture here, the attention only transformer, each layer only consists of multi-head subspace attention and a skip connection. And sometimes this layer normalization can be incorporated to enhance performance, especially for the language tasks. Okay, so and in here, what I want to emphasize is about the theoretical results based on this model and the denoising operator. That is, we can show that actually each layer of this attention-only transformer is doing the denoising. We can theoretically prove it. So here, first we need to introduce a metric, denoising metric, that is signal-to-noise ratio, right? Like we said, for each layer, you can see here, for each token representation, initial token representation, right? This is signal part. This is noise part, right? Then based on this, we can introduce the following signal to noise ratio, this metric. What is the this part is UK equal transpose of the all the tokens, right? The tokens belongs to K subspace. This is signal part, the magnitude of signal part. This is the magnitude of what? Of the noise part, right? Signal over noise. That is why we say it's a signal to noise ratio, this metric. Any questions? This metric, a key component in our analysis. Okay, you can see then we record the data assumption for the tokens, initial tokens. This is the first layer, denotes for initial input layer, right? This is UKAI, and this is the noise part, right? This is signal part. And here we make some other assumptions about the latent, this variable, latent vectors. We assume this latent vectors AI to be standard multivariate, standard normal Gaussian vector, and the EIJ also the standard normal Gaussian vectors with the noise magnitude delta. And this delta usually smaller than 1. Okay, for this assumption. And also have some independent analysis for some independent, also have some independent assumption on this noise vector and also signal vectors, right? To facilitate our theoretical analysis. Okay, independence. We assume AI and EIJ, right? All of these vectors are respectively mutually independent, and AI also is independent of EIJ, okay? And also to further simplify analysis, we'll assume the subspace dimension, the latent dimension to be same, and the number of sample in the class is n over capital K, okay? And this subspace U1 to UK to be orthogonal to each other. Okay, these assumptions. Any questions? Then based on this assumption, we can use the concentration analysis. Well, I think whether you guys heard about concentration equality. Concentration equality from the high dimension statistics. I think Professor Ma, his last book, right? High dimension, that book, the data analysis has a lot of, in the appendix, has a lot of concentration inequalities. That is to like, when you have lots of the random vectors, they have some asymptotic, non-asymptotic good behaviors. Okay, then we can use the concentration equality to show the following result. That is, suppose this operator, this here, this phi, this operator. This is like a composition of softmax of some and also some other the specialty, the composition of this operator. And then we show that with high probability, the signal to noise ratio, this metric, okay, is layer-wise increasing. You can see here, the signal to noise ratio at L plus 1 layer over signal to noise ratio L layer is equal 1 plus eta times tau. This eta is like step size tau is this specialty. That means what? That means signal to noise ratio is layer-wise increasing. Each layer of attention only, our constructed transformer is doing denoising, and this denoising performance can be measured, can be proved, right? Denoising performance can be proved by this equation, by this theory. And also we do some realization for signal to noise ratio. The performance, you can see this is number of layers, right? Number of updates, 2, 3, 4, 5, 6, 7, right? You can see as the layer index increase, this signal to noise ratio gradually increase, this circles. And this fatal line is derived from our sporadic bound. Any questions here? Yeah, this is a really interesting sporadic justification on our principle designed the attention, right? The transformer architecture. Like in Crete, that part, although we designed this transformer, but we cannot do any like principally like sporadic analysis for the what essentially each layer of neural network doing, cannot give a very quantitative analysis. Here we close this gap. We show that actually each layer of this white box transformer based on the multi-head subspace self-attention is doing the denoising, increasing this signal to noise ratio layer by layer at a linear rate, right? Okay. That is the attention-only transformer. Any questions? Actually, in our this result is from our last year SML paper, and in that paper we also do lots of like real-world the experiments, like train this transformer on different tasks, like the reading task and also language task, and take a look at the performance. Due to the architecture, we can also achieve the good performance on different tasks comparable to the like Crate. Although it's much more simplified compared to the standard Crate architecture. Okay, if you are interested, you can take a look at the paper. And another simplification, a variant of the Crate is the linear attention, the transformer. Linear attention based transformer. The full name is token statistic transformer. Well, and this is also a new transformer attention operator, and we proposed based on the rate reduction, and it has a great advantage compared to the standard Crate architecture because its computation complexity scales linearly with the number of tokens based on the coding rate objective function. Now, we will take a close look at how we can derive this objective and also derive a linear complexity transformer, token statistics transformer. And we call that in the last lecture, we will apply this Crate to the supervised learning task, right? We will use a assignment matrix, right? That is a soft assignment like we denoted at pi, and the pi's have k columns, and this matrix this should be capital K, denote total numbers, and the k is denote the solved assignment of this sample is like capital N times K of sample to cluster solved assignment, and the summation of each column, each row is 1, right? The rows are probability the vectors. Okay, and the weight reduction based on this assignment is for supervised learning. If this pi is no, it's like this, right? Of course, here we we use this vector in our previous lecture 7. In our lecture 7, we use the matrix. They are one-to-one correspondence to each other. Okay. And the objective function is like this, right? And note that here we won't assume this pi k is null. We won't assume this pi is null. Okay. In supervised learning, in supervised MCR for supervised learning, MCR2 for supervised learning, we assume this capital pi is given. But here we won't assume it's null. Okay, it's not given. Okay, and then in the previous result, in our recent paper, in Professor Ma's recent paper, actually is this year the iClear, I believe it's a spotlight paper. Anyway, I forgot is or spotlight a paper. The derived variation form is from this one token statistics transformer. This paper linear time attention is variation rate reduction published on iClear this year. And they derive very interesting result based on the variation form. That is, for any orthogonal matrices, this one, the compression chain can be bounded by its variation form. And this variation form compared to the original form is much more complicated. That is, have like UK transpose diagonal pi k, UK transpose some term like this. And this is the diagonal elements of this matrix. But you can, it's easy to note that what's difference from the standard here, this other compression chain here, right? Here, these log determined. Oh, sorry, this is should be, I forgot ZZ transpose here. Here, there should be a ZZ transpose. Sorry, I forgot it here. Okay, so what's the difference from this variation form from the original, the compression chain? We remove what from determined, right? We introduce what? We introduce a UK, right? A bunch of UK, right? To remove this determined, right? This is what we said, the variation form. So based on this simplification, based on this variation form, we can further like use the same approach as we derived in the grade. We can first like compute the gradient of variation form. It's much more complicated compared to the original, the grade, the updates, the variation form, the gradient, right? You can see it's like this form. It's very complicated. UK like it times a D matrix based on this D matrix is defined like this way, and this operator circle, like this circle operator, means element-wise operator. It's like element-wise square. Okay, element-wise square of this matrix, and this is like element-wise inverse for this matrix. Okay. Is element-wise operator. And a very straightforward approach to construct the neural network is doing what? Based on this, is take a gradient step on this, right? And then construct neural network. But here, a key component is doing what? Is to estimate, like we said, since the cluster membership is unknown, so a key step is to estimate the cluster membership pi from this representations at each step. You can see here, how do we estimate this cluster membership? Actually straightforward, is doing softmax, and at each, you can see softmax at each row, right? At each row, and each row inside the softmax is what? Is a projection of this data on the K subspace. And this is exactly what we have talked about in the last class, right? How to estimate, how do we implicit estimate the cluster membership? How do we, if this token is approximately lies on the some subspace? I can give an example, you can take a look. Suppose we consider ZI, these tokens, right? This token representations, okay? ZI. Okay, ZI. And I belongs to like C case subspace. So what is, if the I is like a union of lies on a mixture of Laurent Gaussians. So ZI equals to what? Right? Evaluate times AI. Right? So if we do the projection on different bases, suppose we impose assumption that is, suppose this is assumption, the covariance assumption that UK transpose UR equal to 0 for any case, or maybe close to 0. Okay, so we do like operator here, do operator, right? They project this I on the I onto different subspace here individually, right? So if we project the Zi to case subspace, we get what? AI, right? And AI is follows what distribution in the latent space? Latent Gaussian. Approximately, if you do a computation, the normal expectation of this norm is what? Is P, right? And if we project the Zi onto other subspace, right? Else subspace, we get what? Zero, right? Drag on other subspace, we get 0. On the subspace it belongs to, we get the length, the signal magnitude is P, otherwise 0. So that is why I say you're doing this like implicit compute the membership, right? Okay, that is the geometric interpretation for this step. Well, based on this step, we can further derive this token statistics transformer, the updates is like subspace self-attention, but the difference is this updates is from here, the gradients computation here, right? This gradient computation, then the self-subspace attention is this, but this pi k is computed by this formula, This pi k is computed based on this formula, and the k denotes the case column. Okay, that is, we can estimate the membership from the token representations at each layer. Any questions? This is the key component of the token statistical transformer. Okay, if not, we go ahead. Then we can further write down plot realize the whole map, whole architecture of the token statistics transformer. You can see here, this is some input tokens, right? First dual normalization, and this is token statistical self-attention. Exactly, implementation of this corresponds to this updates corresponds to this architecture. First, to do some, we have k heads, right? Each head do the projection. Projection is to what? Is like to implicitly find the membership, right? And then do that one diagonal attention. Here, diagonal attention compared to standard attention, right, can save a lot of memories. It's much more efficient. And then do a pi membership aggregation and get the output. Okay, and the complexity here, space complexity is P, time complexity is NP. N is the number of tokens. So you can here, we compare write down the time and space complexity of the attention operators in different transformer architectures. You can see here, T, the computational complexity is what? Computation complexity is Pn squared. N is total number of tokens. P is dimension of tokens, right? And norm N squared P, right? And memory complexity is N squared. Okay, and crate is same. p np squared, the order, right? N squared. And CIT, right? XCIT, this is C squared. But host here, based on the memory, based on this, see the diagonal, that the attention, that operator, we can save a lot of memory, and the time complexity, computation time complexity is n times p, and the memory complexity is p. Okay, that is why we call it the linear time attention. Okay, and then we also do lots of experiments for these transformers. You can see here. Although we can save a lot of memory, but we can still achieve good performance. We compared it with some other linear time transformer, like say Performer, Linear Firmer, Big Bird, Reformer. This one we can find it. At least we can claim we can achieve comparable performance to other linear time transformers on these different tasks. Okay, and also we implement the toast like tiny, toast small, toast medium, right? Lot of with different number of parameters like 5 million, 22 million, and also 1680 million, and compared to the some other like XCIT small, YT small, and you can see here we can achieve comparable performance on ImageNet, ImageNet Real, and also Silver 27, Silver 100, Oxford, Flowers, and this different data sets. Any questions? If not, we finally we briefly sum up this lecture. And actually, the whole slide of this lecture is based on our content of the textbook Deep Purpose Learning. This textbook, the learning deep representations of data distribution. This online book, the chapter chapters 4.2 and 4.7. And when I make these slides based on this chapters 4.2, 4.3, I spotted lots of errors and typos. So if you guys, when you read the book and also do some exercise in the book, this online book, please let us know. You can send an email to me or to Professor Mao and any also here, or make an online pull request for the GitHub that repo. And report the error and also report any mistake you spot when you read the book. We really appreciate it. Okay. Any other questions? Okay, if not, we can stop here. Don't forget to take attendance, right? Thank you.